this soft drinks canning factory, over 9 million cans are produced and distributed each week. The canning and packing process is a high-speed, continuous operation. These empty cans are filled at a rate of over 1,400 cans a minute. The manufacturer has to ensure that he doesn't underfill or overfill his cans, so he needs to monitor his production process very closely.
Whenever you buy a pre-packaged item of food or drink, you'll find written on the packaging a number of items of information. For instance, the name of the product, its ingredients, and the weight or volume of its contents. In this case, the can has the volume printed on it, 330 millilitres. I'm going to pour this into a measuring cylinder. Now, with the high-speed production process we've just seen, you may wonder how accurately the manufacturer can control the volume he's putting into the cans. Can I expect to get exactly 330 millilitres? Let's see. Well, this can actually contained about 328 millilitres.
We know from that sample of one can, we can't expect to obtain exactly 330 millilitres. Indeed, another can would produce a different volume again. In fact, if I want to draw inferences about what I might expect to get when I open any can, I should obviously look at a sample of cans. This is what we got when we measured the volumes of 10 cans. The smallest volume was about 328 millilitres, and the greatest, nearly 336 millilitres, with quite a spread in between. So now I can get some sort of feel for how the volumes are distributed. But if instead I'd chosen a different 10 cans in my sample, would I still come to the same conclusion? Here are another 11 samples, each consisting of 10 cans. This top one is the first sample we took, the one you've just seen. All these other samples were taken a few minutes later. Would I come to a different conclusion if instead I'd obtained one of these other samples? Well, none of them are quite as spread out as that original one. This one has a lot less spread. Before we jump to any conclusions, it's useful to attempt to find out whether these data come from one of our known distributions. Well, we can regard these 12 samples of size 10 as one sample of size 120. Let's summarize these data, all 120 observations, into a histogram. This is what it looks like. You can see it has the right kind of shape to have come from a normal distribution. But could it reasonably have come from a normal distribution? We can try looking at the skewness, which we'd hope to be not too far from 0. Well, minus 0.11 is pretty good. And the pointedness, we'd hope to be close to 3, and it is. But how close is close? Obviously, samples will differ from the theoretical. Let's look at a simulation.
The computer has been set up to generate samples of size 10 from a normal distribution. So I'll use these values in my computer-generated distribution and see whether they look like the ones we got before. It's displaying them in exactly the same way. Each line represents a sample of size 10, and there are 12 of these samples altogether. Again, some samples are rather more spread out than others. Let's take the observations from all 12 samples, that's 120 observations, and plot them on a single histogram like we did before. The histogram isn't as regular as you might have expected, and the skewness and pointedness aren't all that close to our desired 0 and 3. But nevertheless, we do know that these observations actually come from a normal distribution. We'll see how this histogram compares with the one we got for the sample of cans. They aren't all that similar. But the computer can go on generating samples from this normal distribution. And clearly it's easier to compare sets of 120 observations rather than individual samples of 10. Let's compare each of these with that histogram we got from the 120 cans. Well, they're not all that much like the sample of cans, but that one's quite similar. But the message we're getting from this is that even though we know the parent distribution is normal, there's a great deal of variability. And it's obviously quite plausible that our original sample could come from a normal distribution. You can see that even when sampling from a distribution we know is normal, there's a fair amount of variation for this sample size of 120. So it wouldn't be unreasonable to expect a similar amount of variation when looking at our data for cans. Of course, our computer-generated data is much more regular if we look at an even larger sample. Here are the 10 computer-generated histograms, each with 120 observations. Let's amalgamate all of these observations into a single histogram. This histogram represents all 1,200 observations that the computer generated, and it's quite regular. And if we superimpose the curve of the normal distribution from which the observations were drawn, we can see that we do indeed get a very good fit.
So, from all that, it's not unreasonable to assume that the sample of cans did actually come from a normal distribution. Now, one thing may have been puzzling you. You probably noticed that some cans do actually contain an amount less than the 330 millilitres stated on the can. You may have been wondering whether the manufacturer is allowed to produce cans that are deficient in volume. Here's Eric Gordon, the plant chemist for the Coca-Cola Export Corporation.
There is a series of directives issued by the EEC, the purpose of which is to ensure that the customer gets a fair deal. It is my duty as a manufacturer to be able to demonstrate that I'm complying. One of these directives is of particular interest to me. In it, it states that each hour's production, the actual contents of the packages shall not be less, on average, than the nominal quantity. Here, the nominal quantity is that written on the side of the can, 330 mils. This means that to comply with the directive, each hour's production, the average volume must be greater than 330 mils. This allows me to fill individual cans which contain less than 330 mils. However, the overall hourly average must be over 330 millilitres. In order to comply with the directive, I have to frequently check that the average volume is over 330. Now, it is impractical for me to check every can I fill. So what I have to do is to take samples.
So the manufacturer wants to know as soon as possible if the average volume falls below 330 millilitres. So what he does is take samples at regular intervals, and if he gets an unusually low series of volumes, he'll take action to rectify his production. Because the EEC regulation requires that the hourly average, or mean volume, should not be less than the nominal quantity of 330 millilitres, he'll not be unduly alarmed if a single can contains less than this. Notice now that the emphasis has shifted from the volume in one can to the mean volume of a sample of cans. From the random variable x, the volume in an individual can, to x bar, the mean volume of a sample of cans. So let's look at the means of the samples of cans we had earlier. Here are the 12 samples that we displayed on the board. I'll get the computer to work out x bar, the mean of each sample, and mark it in red on the diagram. So these are the 12 sample means. Let's put them all together on one line at the bottom. What do we notice about the distribution of the sample means?
The most obvious thing to see is that the spread of the random variable x bar is much smaller than the spread of x in each of the 12 original samples. Each of the sample means is located very close to 331.5 millilitres, which is the sample mean for the whole 120. You can therefore see that the distribution of mean volumes of a sample of 10 is much less spread than the distribution of the individual cans. We've seen that it's reasonable to take the distribution of volumes for individual cans to be normal, but what we now want to know is what should we take the distribution of the mean of a sample of cans to be?
Here are the 12 samples, each of 10 observations, from the normal distribution which the computer generated for me earlier. And now we'll mark in the mean of each of these samples and put these means onto one line at the bottom like we did before. Now I can enter these means into a histogram, but we can't see a pattern from only 12 sample means, so what I'll do is take a lot more samples and put the sample mean of each onto this diagram. This is what we get after we've entered 1200 sample means. It has the shape we've come to expect from a normal distribution, so we'll fit a normal curve to it. Finally, let's compare this fitted normal curve for the sample means with the fitted normal curve for the individual values.
Here are the same two curves. This is the normal PDF we fitted to the individual cans, and this is the normal curve we fitted to the means of samples of size 10. As we can plainly see, the distribution of means has much less spread than the original distribution of individual cans. But the interesting thing is to try to see how they are related. It's fairly obvious that both of these distributions have the same mean. And it's equally obvious that they don't have the same variance. For each of the distributions, I've marked in a line at one standard deviation above the mean. By measuring these standard deviations with this ruler and squaring them, we can compare the spreads by comparing the variances. If I call the standard deviation for the distribution of the mean 1 unit, then the standard deviation for the individuals is just over 3 units. Looking at the sigma squared scale, then 1 squared gives 1, and for the individuals, sigma squared is 10. Now, this is interesting. We obtained the means of samples of size 10, and when we compare the distributions, we find the ratio of the variances is 10 to 1. Does a general principle operate here?
Here's the normal curve representing the distribution of the individual volumes. And this is the distribution of sample means for samples of size 10. The ratio of the variances is 10 to 1. Now let's look at some distributions of sample means for samples of other sizes. This is the distribution for a sample of size 4. Again, it's normal. The ratio of the standard deviations is 2 to 1, and the ratio of the variances is 4 to 1. Now for a sample of 25. The ratio of the standard deviation is 5 to 1, and the ratio of the variances is 25 to 1. And for a sample of 36, as you can see, as we increase the sample size, the standard deviation of the distribution of the means becomes smaller and smaller. And generally, for samples of size n, the ratio of the standard deviations is root n to 1, and the ratio of the variances is n to 1, or, equivalently, 1 to 1 over n. What we've seen is that the sample means for any given sample size are also normally distributed. The mean of this sampling distribution is the same as the mean of the parent distribution, and as the sample size gets larger, the standard deviation gets smaller. In fact, these results generalize to any normal distribution. We'll summarize them as follows. If x has a normal distribution with mean mu and variance sigma squared, then x bar, the mean of a sample of size n, also has a normal distribution, with the same mean, but with variance only sigma squared divided by n. That is, the ratio of the variances is 1 to 1 upon n. So we can gain information about the mean mu by looking at the means of samples. And clearly the larger the sample size, the better, since the variance of the sample mean is less for a larger sample than for a small one. In other words, it's better because the distribution is more concentrated about the mean. So how can the manufacturer use this information about the distribution of sample means to ensure his cans contain, on average, at least 330 millilitres?
What the manufacturer wants to do is stop the production line if he's pretty sure that the production mean has fallen below 330 millilitres. That is, as soon as he's sure that the distribution of volumes has a mean lower than 330. He wants to be able to detect a shift of this curve to the left. He wants a hypothesis test, the null hypothesis being that the mean is 330 millilitres against the alternative hypothesis that the mean is less than 330 millilitres. The manufacturer knows that over the last few days his standard deviation has been 1.72 and is likely to remain the same. Now, if he takes a sample of 10 cans and measures the mean volume, the distribution he'd expect for x bar under the null hypothesis is normal, mean 330, variance 1.72 squared divided by 10. Here is this distribution. Once we know the distribution under the null hypothesis, and we do, we have everything we need to calculate the critical region. We're not going to do the mechanics of that here. We'll be doing that in the remaining 2 sections of the text. In practice, you'll find the first thing you do is standardize the random variable. And then you can use the standard normal tables. You'll find, in fact, that if you do a test at the 5% significance level, the critical region is x bar is less than 329.1. So the manufacturer would stop the production line and adjust his filling machine if he got a sample mean below 329.1.
We've seen how the manufacturer can check his production to ensure that he's meeting the regulation. But the government, who enforce the regulations, don't just take the manufacturer's word for it. There's also a body of people whose job it is to ensure that regulations such as this are enforced. This is the local Weights and Measures Authority.
As an inspector of weights and measures, I have the authority to enter the premises of a manufacturer and to carry out tests to show that he is complying with the provisions of the Weights and Measures Act. Like the manufacturer, I also take a sample, but I cannot take the sample in the same way that the manufacturer does, because I cannot rely on the information that he gives me on the population variance, because I cannot confirm these figures for myself.
We've seen that the manufacturer uses this formula to transform the sampling distribution of means into a standard normal distribution. But the Weights and Measures inspector can't do this, as he doesn't know the value of sigma, the population standard deviation. But what he can do instead is transform using the sample standard deviation S, and then he uses this formula for T, with S replacing sigma in the original formula. However, since S is calculated from the sample, then T can't possibly have a normal distribution. Let's see what its distribution is like for samples of size 10. Earlier in the programme, we got the computer to generate samples of size 10 from a normal distribution. Here are the same 12 samples. For each sample, we've worked out the mean, x bar, and the standard deviation, S. Now we can work out the value of T for each of the 12 samples. We can put these values of T in a histogram. But to get a good idea of the shape of this distribution, we'll need to take a lot more values. Now we can see the shape of the distribution, so we'll fit a curve to the histogram. Let's compare this with the curve of the standard normal distribution. Our curve looks very similar, but if we look closely at one of the tails, we can see that in fact the tail of the t-curve is larger than that of the standard normal distribution.
So we've seen that the distribution produced using the sample standard deviation in place of sigma isn't normal. In fact, the curve you've just seen is called a t-distribution. You'll be investigating the t-distribution after the program. There's only one standard normal distribution, but there's a whole family of t-distributions, one for each sample size. We've just looked at one of them, the one for a sample of size 10. Here's another one. This is for a sample of size 50. For every different sample size, there is a different t-distribution. Whatever the mean and standard deviation, we always get this distribution provided we take a sample size of 50. So generally, provided the original parent distribution is normal, if we don't know the population standard deviation, we can use the sample standard deviation, and then use one of the t-distributions. Now, why are we looking at the one for a sample of size 50? Well, this is the sample size that the weights and measures inspector uses. Like the manufacturer, he tests whether the population mean has fallen below 330 millilitres. But he wants to be very sure that the population mean actually is below 330 millilitres before accusing the manufacturer. So he'll only fail a batch if he gets a value of t somewhere in this left tail. The weights and measures inspector sets his significance level at 0.5%, a very much more stringent level than the manufacturer sets for himself. So the weights and measures inspector will only fail the batch if he gets a value of t which lies within the lower 0.5% of this distribution. You'll learn later in the unit how you can determine where this lower 0.5% lies from your statistical tables. But here I've calculated it by looking at the area under the curve. Here it is. If he calculates a value of t from the sample using this formula, and he gets a value of t less than minus 2.68, then the batch fails, and the inspector concludes that the manufacturer is not complying with the EEC regulation. Otherwise, he passes the batch. Well, let's see what happened when the weights and measures inspector took his test.
For my test, I take a random sample of 50 cans over a 1 hour period. I use a computer-generated list of times and select the can which is passing at that moment. Each can is weighed and the computer calculates the volume of its contents. It does this by subtracting the constant weight of the can and adjusts for the known density of the liquid. When all 50 cans have been measured, the computer prints out its analysis. It gives the mean and standard deviation of the sample and the most important information, whether the group has passed or failed the test.